Welcome back. In this lecture, we're going to examine several functions which calculate crucial statistics about the distribution of a dataset. These include the mean, variance, and standard deviation, and each one comes with a designated function. Now that we have a plan in place, let's get coding. We start by importing NumPy and defining a 2D array called matrix A. Okay, then we'll examine the median function. It takes an input array and returns its median value. If you don't remember what the median is, it's just the middle value of a sorted dataset. If there are an even number of elements, it's the average of the two middle ones. Let's call the median function and pass matrix A as an input argument. The output is 3, which suggests that when all the values of the array are sorted, 3 is right in the middle. To check if this is accurate, we can once again use the sort function and set the axis to none. Conveniently enough, the 7th, 8th, and 9th elements of the array are all equal to 3, so the output is correct. Next up is the mean function. We already examined it in depth at the beginning of the section, but we need to mention it here as well. The mean function calculates the arithmetic average of all the values in the dataset. We've already seen how it works, so we're just going to call it. Now, we've seen the output as equal to 3.4, but we want to have it on the screen when we introduce the next function we want to examine, average. Just like mean, average computes exactly what it states, the average. Hence, if we call the average function and pass matrix A as the input, then we get the same result as mean. So, why do we need to have two different functions then? Well, average can compute the weighted average of a dataset, meaning it's more versatile than mean. Let's see how our output will change as we create an array with weights for each element in matrix A. We can set these values manually, or we can use a random generator to randomly create an array of weights. Since we've already discussed how random generators work, I'll opt to use random weights here. So I'll execute this cell to import the generator and PCG64 modules, as well as create an array called array weights of the same size as matrix A. And that will contain the randomly generated weights with a seed equal to, guess what? 365. In the next cell, we can once again call NP average, but this time set the weights argument equal to array weights. Once we run the cell, we get a value that is different from the output for a mean. Thus, we can safely say we've arranged to assign weights to each element. Bravo! In the beginning of this lecture, we talked about the variance, so it's time to take a look at its function. The name is VAR, which of course is just short for variance, and just like mean, it only requires a single input, the dataset. Hence, let's call NP VAR and plug in matrix A as an argument. The output is a single number, meaning the variance of the values of the flattened array is 7.84. Since all the outputs so far have been correct, we'll just assume this one is too. We don't want to spend more time testing the accuracy of functions that have been staples of NumPy for years. The next and last function we want to examine is STD. Medical abbreviations aside, the name of the function stands for standard deviation. Thus, we can go ahead and call np.std and pass matrix A as an input. The result is 2.8, which looks about right. To make sure it's correct, we can bring 2.8 to the second power and see how accurate the result is. If we ignore some minor rounding issues, which only reflect estimations and how Python has been programmed to display such results, we can clearly see that the square of the standard deviation is equal to the variance. Hence, we can conclude that the function works as intended. Fantastic! Now that we've seen how to compute the mean and the variance of an array, it's only natural to want to know how to compute the covariance of two arrays. And that's exactly what we'll do in our next lecture. Thanks for watching!